All right, hello everyone. I just want to cover a few examples in this video that are going to be very useful for the test. And this is to supplement the two class kicks that we had for reviewing 1D forces and also the Kahoot that we did in class. So with this video, the class kicks and the Kahoot, that should be more than enough to be completely prepared for the test that we're going to have next week. So some things I want to talk about. First is friction. So I want to talk about friction and go over a little bit more detail about how friction fundamentally works. I'm going to basically go over the simulation that we did during the friction discovery lab, so the PhET simulation. And once I clarified some of those concepts, we can do some examples with skydivers and elevators. So let's look at skydivers and elevators, right? And then we're going to look at some specific tension examples, right? So some specific cases when dealing with tension that are important to know. And then we're going to be also looking at an example of the third law. This is going to come from the third law class kick. And then there's another one for Atwood's machines. So I'm going to go over these examples in detail to make sure that you know how to approach the problems. And so let's start with the friction. So here I have friction. Wait, what am I doing? That's not it. Let's see here. So here I have some friction with this simulation. So if you remember in class, basically the way this worked is we played around with the sim in order to discover how friction really works. And one of the first things that we found is that the friction force, when the box is not moving, the friction force is going to equal the applied force, right? So those are the only forces acting on the object. The friction force is going to balance out. Oh, I got to refresh this. There we go. So right now I have these 5 scenarios. Click the forces, some of the forces, values, massive speed. Basically all the information's up. And right now the sum of the forces is 0. There's no friction, there's no applied force. But as I start applying a force on the box, what you should notice is that the friction force is going to equal the applied force, right? So I'm applying a force of 50 newtons, and the friction force is pushing back with 50 newtons, all right? If I apply even more force, I apply 100 newtons of force, the friction force is also 100 newtons. Now, this is not going to continue indefinitely, right? At some point, if you push something hard enough, it will move. But this is to highlight some important facts about friction. First of all, that technically there's 2 types of friction. So there's static friction and there's kinetic friction. Okay, so static friction is what we're seeing right now. This is when the box is not moving. You have the surface of the box and the surface of the road. They're in contact, and basically they're not moving with respect to each other. At some point, there's going to be enough horizontal force applied to the box to where it's going to slip, right? So there's a static frictional force between the box and the road, and if I apply enough force to it, eventually it's going to slip, and we're going to enter the regime of kinetic friction. So let's see what happens. So right now I have 100 newtons, and the box is still not moving. So I'm going to apply a little bit more force to the box. I'm not sure why it's not working. Okay, that's weird. It should be working with this. I guess not. Okay, so we apply 50 newtons of force, then we apply 100 newtons to push it back with 100 newtons, and I'm going to slowly increase the friction, the applied force. And we see the friction force keeps matching my applied force up until a critical point, and I believe it's here. So at this point, the friction force, the static friction force, is reaching its maximum. All right, so if I apply any more force to this object, it is going to slip, and it is going to begin moving to the right. All right, so let's see that. So I'm going to apply some more force to it. As soon as I apply 126 newtons, notice what happened. Right, so I'm going to bring it back down to 125. Actually, it doesn't necessarily work that way. I got to really let it slow down to a stop. So now it's stopped again. We're in the regime of static friction. I start increasing the force. The box still isn't moving, but as soon as I pass the maximum static frictional force, it begins to slide. So it slips, and now my net force is 32 newtons. And notice how much the friction force dropped. The friction force went from 125 all the way down to 94. All right. So this is one key fact about friction, right? So if I go back to here, so there are two types of friction. So two types of friction. Okay. There's static friction and there's kinetic friction. So the static friction, again, is when the surfaces are not moving, right? They're static, okay? So I'm going to say this is when the velocity is 0. So the velocity between the surfaces are 0. That's we're in the realm of static friction. And then the kinetic friction is obviously once it starts to slide. So there's this point where the objects are going to slide past each other. They're going to slip. And that's where it goes from static friction to kinetic friction. So let's actually make a plot so we can kind of visualize what's going on. So I'm going to go back to the simulation. And here we see the box is not moving. I'm going to apply some force to it, get all the way up to 125. And as soon as it reaches 125, boom, the friction force decreases to 94 right after slipping. And it stays a constant 94. It doesn't matter how much more applied force I add to it. I can go to 150, 200, 250. The friction, the kinetic friction stays at 94 newtons. Now, obviously, this box is going to accelerate like crazy. Eventually, I think the guy falls down. Yeah. So here's something else that's important to know. So we know the kinetic friction is constant. In this case, is based on the force between the box and the ground. And we'll go into more detail about the equation later in 2D motion, or 2D forces. But for now, we just need to understand the concepts behind friction. So one other important concept is that friction opposes motion, right? So we notice here, I'm going to start pushing the box to the left, right? And then I'm going to stop pushing. So I'll go to 0. Okay. Now notice the box is moving to the left. Friction's going to the right. All right. And when I'm going to push it, give it some speed to the right, and then I'll stop. So now the box is moving to the right, but the kinetic friction is going to the left. So friction opposes motion. It goes opposite the direction of motion of the object. Okay. So let's go back here. Okay. So I'm going to make a little plot just to really make sure we know the difference. So here I'm going to have my friction, and then here I'm going to have my applied force. So my force applied. All right. And let's see what happens. So my friction is going to match my applied force, my static friction, that is, and they're going to equal. All right, so the static friction is going to equal the kinetic friction up until it hits some important value, right? So this is when it starts to slip. So here, that was at 125 newtons, and at this point, it's the max static friction, and that's basically when it slips, right? So the max static friction is the point at which it slips. As soon as it slips, it immediately drops down to a lower value. And I believe that was, 94? So 94 newtons. And then it just continued going like that. So actually, I'll use a different color. Sure. So now at this point, it doesn't matter how much more force I apply, it stays at 90 newtons. So this region here, this is when they're sliding past each other. This is the kinetic friction. All right. And this here, this is the static friction. And I'm not going to bother with the equations for now because you don't need them for the test. We'll go over them in more detail in the next unit. But these are some things that you need to know. Also, friction opposes motion. So friction opposes motion. Okay. So that's, yeah, so that's pretty much all you really need. The fact that kinetic friction is some constant value and the static friction varies up to some maximum value, and then at that point it slips and it becomes kinetic friction. All right, so now let's go over skydivers and elevators. There are some of these in the review, but I really just want to make sure we got it. So, quick example with skydivers, right? So let's say we have a case where we have 100 kilograms, okay, 100 kilogram skydiver. and he's experiencing some air resistance as he's falling through the air. Obviously, he also has a weight force, right? This is going to be the force of gravity, the weight force. So remember that weight is equal to mass times gravity. All right, that's very important to know. All right, and that's basically what the force of gravity is. So the force of gravity that the Earth exerts on us is our weight. All right, so F sub g is equal to mass times gravity, where the surface gravity on Earth is 9.8 meters per second squared. And that's the acceleration due to gravity on planet Earth. So here we know he has a mass of 100 kilos. We're obviously skydiving on planet Earth. So this force, if I write down what the forces are, let's say we have 500 newtons of air resistance, and we would have 980 newtons of the weight force. All right. So say you had a problem that was like this, and you need to calculate the acceleration, right? So find the acceleration of skydiver. All right, so I know that y'all can do this, but let's just go over the conventions. So here we know that this guy is going to be accelerating downward because the force of gravity is greater than the air resistance. So he's going to have a net force going down. And let's just set up Newton's second law. So we know that Newton's second law is F net is equal to ma. And it's also equal to the sum of the forces. So I'm going to add up all the forces that are on my free body diagram. And I have 980 newtons going down, the force of gravity, minus the force of air resistance. All right. So I'm going to use the convention where I call the direction of acceleration positive. It's a very useful convention. And since the gravity is larger than air resistance, he's going to be accelerating downward. So the gravity is going to be positive. Air resistance will be considered negative. So let's just plug in the values. So here I have 100 kilograms, right, times the acceleration, whatever that is going to equal 980 newtons, right? That's his weight minus the air resistance, which is 500 newtons. Right, it's going the other way. And just do the calculations. So we end up with 480 over here. For the net force, that's the sum of the forces. And we know Newton's second law says that has to equal the mass times acceleration. And I end up with an acceleration of 4.8 meters per second squared. So that one's pretty simple. Let's do another one with elevators, right? So elevators, something that's important to know. It's basically all these problems have to deal with standing on a scale, right? So say we're on an elevator and there's a little scale here, and we have a person just standing on the scale in the elevator, okay? All right, so let me put a little rope here. So when you stand on a scale, obviously it tells you what your weight is, but the reason it does that is that scales, right? So like a bathroom scale, it reads normal force, right? So a scale actually tells you the normal force. I'll say scale measures normal force. All right. And just so happens when you're in your bathroom, right, obviously you're not accelerating up or down, or at least I hope, so you're going to be in equilibrium. The forces have to balance. So the upward force, the normal force that's holding you up as you stand on the scale, that's going to equal the gravitational force that's pulling you down. Now, on an elevator, if you're accelerating up or down, well, that changes the situation, right? So one example would be, let's say that you have, mass of 100 kilos. So, same guy. So the guy went skydiving, and now he's on an elevator standing on a bathroom scale. So this is a quirky dude, but that's what he likes to do. And he has a mass of 100 kilos. And let's say the scale reads, so the scale is going to read, all right, I'm going to make up a number that's kind of easy to calculate. So let's say the scale is reading 1,480 newtons. All right. So in this case, we need to calculate. Oh, actually, that doesn't make any. We could do it like that, but let me choose a different. Let me fix this real quick because I want to make the numbers nice and neat. So I'm just going to say the scale reads 14,800 newtons. All right. So the scales, oh wait, never mind. All right, we're going to stick with the original number. I'm just trying to pick a number that makes the example very easy to see. So 1,480, that's what the scale reads. So let's examine the forces acting on this person. So we have a normal force holding him up, right? This is my normal force. And then we have a weight force, right? So that's just the force of gravity that's pulling him down. So let's calculate what the net force is on the person. And then let's also figure out what the acceleration is, okay? So in this case, we know the normal force is 1,480. The gravitational force is going to equal m times g, right, which is 9.8 on Earth. So we have the 100 times 9.8. It's the same guy, right? So the same guy as a skydiver. He weighs 980 newtons. So he has a weight of 980 newtons. The scale in the elevator is reading 1480. So it's very similar to the skydiver problem. So we know that that equals ma, and that is going to equal the normal force minus the force of gravity, right? So in this case, he's accelerating upward, right? So because the scale reads normal force, and the normal force is larger than the force of gravity, we're going to consider up to be positive. That's the direction of acceleration. That's the direction of the net force. And so the way I set up Newton's second law, I'm going to set it up as F normal minus F of gravity. That's going to equal the net force of this person. So let's just plug in the numbers. And we have here 100 kilograms times the acceleration. That has to equal the net force, which is just normal force minus the force of gravity. So that's his normal force. His force of gravity is 980 newtons. All right. So for the sum of the forces, we got 1480 minus 980. That equals 500. All right. So I picked these numbers on purpose to make it nice and easy. So 100 kilograms times the acceleration. And the acceleration is just going to be 500 divided by 100. Right. So we get 5 meters per second squared. And in this case, he is accelerating up. So I'll specify the direction. In the previous example, when he was skydiving, he was accelerating downward, right? So that's his acceleration going downward. And then in the elevator, he's accelerating upward. So his net force is going to be 500 newtons in this case. And his acceleration, right? So they also asked for the acceleration. That's 5 meters per second squared going up. All right, so that's some simple vertical forces, and now let's look at the third law. Actually, we're going to look at some examples with tension. So we took care of friction, we took care of some vertical forces, and now we're going to do some important tension examples. So actually, really, it's just reinforcing that the tension is going to stay the same throughout the entire rope or string or, chain, whatever it is you're dealing with. All right, so the tension is the same across an entire rope. All right, so that's just an important fact about tension. One example, it could be a tug of war, right? So this is a very common misconception. So say we have a tug of war and the people engaging in the tug of war, they're evenly matched, right? So let's say I'm going to call this person 1, this is person 2. And let's say person 1 is pulling with 200 newtons, right? So he's pulling with 200 newtons. And person 2 is also pulling with 200 newtons. All right. So the question is, what's the tension in the rope? Now, this is a very common misconception. A lot of people would think that the tension in the rope would be 400, right? So I got 200 going to the right, 200 going to the left. Some people think it's 400. But that can't be true. So they are evenly matched, right? And what I mean by evenly matched is that they're not moving. right? So they're basically, no one's winning. They're kind of stuck, right? They're not moving. The acceleration is clearly 0. The net force is clearly 0. Now, for the net force to be 0, let's think about what's going on in a tug of war. I'm going to draw a free body diagram for each person, right? So for person 1, obviously he's trying to pull back with 200 newtons, right? So he's pulling with 200 newtons. If we think of this as a force, there's a horizontal force acting on person 1. This comes from them pushing against the floor, right? So yeah, if you try playing tug of war on ice, you're not gonna have a good time. But obviously they have their shoes on, they're pushing against the ground, and that's what's supplying that force, right? So this guy is pushing off the ground, and there's with the force of 200 newtons, but there's a tension in the rope that is pulling him, right? So we are just wondering what that tension is. And then for person 2, same situation. He's just as strong. He's pushing off the ground with 200 newtons, and then the tension is pulling him. So given that tension is the same, I don't know why I keep doing that. So given that tension is the same across the entire rope, all right, this is an important fact, right? The tension that person 1 experiences has to be the same tension that person 2 experiences, right? Otherwise, the rope would break. So here we know that the tension has to be 200, right? So looking at both free body diagrams, I get that the tension is 200 over here, and that tension is 200 over here. So that's what the tension in the rope is, 200 newtons. So I want to mention this. This is a very simple example, but it's just such a common misconception and mistake that I think it's worth mentioning. So now let's do an actual. I'm going to do 2 more problems, and these ones are, I would say, not trivial. You have to really know what you're doing. We have done them before. So there's a problem that uses Newton's third law, right? So action, reaction, and the statement of Newton's third law. And it's really the most simple of all the laws if you really think about it. All it's saying is that all forces come in pairs, right? So if I have 2 objects, let's say A and B, and these 2 objects are interacting with each other, okay? What that means is that object A is applying a force on object B, and the opposite has to be true. Object B is applying a force on object A. So mathematically, the way we state Newton's third law is the force of object A on object B is equal to the negative of the force of object B on object A, right? Equal and opposite. So they apply equal and opposite forces, right? That's what it means to have a force, right? A force is just interaction between 2 objects, and those forces have to be equal and opposite. Now, something to not get confused on this, the way the Newton's third law works is with 2 separate free body diagrams, right? So you have 2 separate objects, and you have 2 separate. It's kind of like the tug of war, actually, right? I guess that's not necessarily the best example, but like the tension. Well, the tension is basically the force between them, right? So this guy's applying 200 newtons of force on the rope, which is being, pulling this guy. So basically, object 1's applying 200 newtons on object 2. Right, I'm saying object, person. So the first guy is trying to pull the second guy 200 newtons to the left, right? And then the reaction is the second guy is pulling on the first guy 200 newtons to the right. Okay, so that's the basic idea. And it's the same as if they're pushing each other as well. But let's get to the actual problem in terms of how to actually solve it. So this comes from the Class Kick day 16. So Class Kick day 16 tension. That was the title. I forgot which number this was, but this is how it came out. It's going to be important for the test, so that's why I want to go over it. So we have 2 objects, mass 1, mass 2, and there's a rope connecting them. And then there is this force here. I'm going to call this T2. All right. So T1 is between them, and there's another tension, T2, that's pulling on the whole system. So I think they gave us T2. So in that problem, T2 is given. It is stated to be 150 newtons. And also the masses are given. So mass 1 is going to be 35 kilograms, and mass 2 is going to be 45 kilograms. So we got 45 kilograms here. And the first question was, what's the acceleration, right? So the first question is, what's the acceleration of the system? So for this one, I can just use the systems approach. And this is basically where I draw a dotted line around the entire system, right? So M1 and M2, they're connected by T1. So the rope in between M1 and M2 is connecting them. And I'm basically going to treat this as one big object, right? So now I'm looking at the M1 plus M2 system, all right? So this approach is very useful for saving a lot of time. If you just look at the whole system, if they're going to be moving together, you immediately get to the final equation using Newton's second law by just treating these internal forces, well, they're internal to the system, right? So both objects are going to be moving together. All I care about is this external force, the T2. So let's actually work through that using Newton's second law. We have that the net force is equal to the mass of the system, so that's M1 plus M2, times the acceleration of the system. They're going to be moving together. They're going to be accelerating together. And that has to equal the external force, which is just T2, right? So some of the forces on the system, there's only one external force that we're looking at here. That's T2, which is equal to 150 newtons. All right, so to solve for it, I turned that off. I don't know why it keeps, yeah, this is annoying. Okay, off, please. All right. All right, so anyways, yeah, let's just actually work through the math. So we need to solve for the acceleration. I have 35 kilograms plus 45 kilograms. That's the, that's the total mass of the system. Right, so 35 kilograms plus 45 kilograms times the acceleration of the system has to equal 150 newtons. All right, and then 45 plus 35, that's just 80. Right, so 80 kilograms times the acceleration is equal to 150. And then the acceleration is just 150 newtons. That's the external force in the system divided by 80 kilograms. All right, and that comes out to just under 20. Here, let me just do that real quick. 150 divided by 80. All right, wait, what am I saying? Well, just under 20. It's 80 kilograms, not 8 kilograms. So just under 2. All right, so 1.875, let's call it 1.88. So it's about 1.88 meters per second squared. All right. If you want to use 2 sig figs, that's 1 point. I think there's 2 sig figs in the problem. It's at 1.9. So anyways, that was the first part. The second part for that problem was what is T1? All right, so part B for this problem is what is T1? All right, now for this one, you actually want to look at the individual free body diagrams for the masses, right? So we know that T2 is pulling on the entire system, but now let's look at the individual free body diagrams. So for mass 1, right? So this is going to be the free body diagram of mass 1. I just have T1 pulling it to the right, okay? We're not going to worry about the vertical forces because this thing's just sitting on the ground. It's not accelerating up or down. We're not in an elevator. We're only going to worry about the horizontal forces for this example. So we have here, this is mass 1, and it just experiences that tension force. For mass 2, it experiences T2, right? That's the 150 newtons, and it experiences T1 pulling it to the left. Now, what makes this easy is we don't have to write out all the algebra to solve for what the tension in object 1 is, because we already know what the acceleration of the system is. Let's say it's 1.9. So this is the acceleration of the system, right? That was the answer in 2 sig figs. So you can just use F net equals ma, because the only force acting on M1 that's actually contributing to the acceleration is T1, right? So F net for object 1 is M1A, okay? And that has to equal the tension. Now we can figure out what the net force is, because we know mass 1, we know what the acceleration of mass 1 is. It's 1.9. We did that in part A. So let's just plug in the numbers. Mass 1 is 35 kilograms times 1.9 meters per second squared. That equals T1. And yeah, let's just do the math real quick. So 1.9 times 35, let's see, 1.87 times 35. Let's say 66, right? So, well, if we use this value, technically it rounds up to 67, right? So let's just say 67. Or if we're going to use the sig fig rules, we end up with 67 newtons. All right, so that's T1. Then I believe part C. Let's look at it. Alrighty, my video cut out in the middle. I'm going to try to merge these two clips together so it all stays as one video, but we're almost finished. So here, T1 breaks at 500 newtons. What does T2 have to be, assuming it doesn't break? So we're just going to look at the equation for mass 1 and the equation for mass 2 and kind of put them together. So first things first, we have here, let me use a different color. So this is the equation for mass 1. All right, so I'm going to put it here. And we're just going to set it up. So M1A is equal to T1. And now we're going to set T1 equal to 500. All right, so here I have 35 kilograms for object 1 times the acceleration. That has to equal 500 newtons, right? And then I'm just going to divide these two values. Let me grab my calculator. So 500 divided by 35, I get 14.28. Let's say 14.3. So A is 14.3 for the acceleration. And I'll report the final answer with 2 sig figs. I'm just going to use 3 for calculations. So we have 14.3 meters per second squared. That's what the acceleration of mass 1 has to be. And then I'm going to plug that into the equation for mass 2. So for mass 2, we have M2A has to equal T2 minus T1. So T2 minus T1, right? That's just this free body diagram up here, right? So this is mass 2. For mass 2, T1's pulling it to the left, T2's pulling it to the right in the direction of the acceleration. So we set M2A as equal to T2 minus T1. So that's, I'm going to put over here so I can look at it. And let's plug in the values. So we know that the acceleration from the using Newton's second law on the first mass, we know the acceleration has to be 14.3. These two masses are moving together. They're going to have the same acceleration. So now I'm going to plug in mass 2 is 45 kilograms times the acceleration, 14.3 meters per second squared, has to equal T2 minus T1, which is 500, right? So if T1 breaks at 500, that's the maximum force for T1. So yeah, just do the math again. So we got 45 times 14.3. I get 643.5. And I'm going to add 500 to it. All right. And I get T2 has to equal so if I use let's use 2 sig figs. So this comes out to 1,143.5, right? So using 3 sig figs comes out to that. I believe the answer in the class kick used 2 sig figs, so I think it just set it to 1,100. Yeah, so 1,100 newtons, right? So this is 2 sig figs. Okay. All right, so that's how you would find T2. And then the very last one is the acceleration of the system is 3 meters per second squared. What does T2 have to be? So if A is equal to 3 meters per second squared, what does T2 equal? And the easiest way to solve this is use the equation that we got from the systems approach. So from the systems approach, we have this in green. Oh, whoops, that is not in green. I gotta click green, there we go. So this equation here, M1 plus M2, that's the entire system, times A equals T2. So I'm gonna bring this down. to here. Okay. So again, the system M1 plus M2 times A, that's the net force on the system. The external force, the only external force is T2. That's acting on the system. That's this free body diagram over here. Okay. Yeah, just plug in the numbers. So 35 plus 45, the total mass of the system is 80 kilograms, right? Times the acceleration, which is 3 meters per second squared. That has to equal T2. Therefore, T2 has to equal 240 newtons. All right, so that's the answer to the last one. Now, finally, let's look at an Atwood's machine example. So Atwood's machine. All right, so almost there. Very last example, we took care of third law and looking at some specific examples where there's more than one object, basically, right? Atwood's machine is similar, right? You have multiple objects and there's a tension in between the two objects. So let's just set it up. There's going to be a question like this. Oops, let me just use normal color. All right, so you got to know Atwood's machine. All right, so let's do an Atwood's machine example, and that'll be it. So I got here M1, M2. This is from the day 17 class kick. So day 17 Atwood's. I don't remember what number it is, but it's the one where mass 1 is 1.5 kilograms and mass 2 is 0.5 kilograms. So obviously the system is going to accelerate like this, right? So we have our acceleration here. This M1 is going to, well, because it's heavier than mass 2, right? The system's going to rotate counterclockwise, right? So M2 is going to accelerate like this. And the tension between them has to be the same. And this is where the systems approach is really handy. So I could look at the individual free body diagrams for M1 and M2 and relate them via the tension of the rope that's around the pulley. Or I can save some precious time and just treat this all as one big system. That's what you want to do with Atwood's machine. So this is all one big system, and the only external forces are M1G, okay? And you have here M2G, right? So this is the force of gravity of object 1, force of gravity of object 2. We know object 1 has more massive than object 2. Therefore, the system's going to accelerate like this. So these are forces that are external to the system. The tension force is internal to the system. So we're not going to worry about it using the systems approach. So this is the way you want to approach Atwood's machine. So the systems approach, right? So we're using, this is the M1 plus M2 system. All right, and we know, as always, Newton's second law, F net equals MA. But this is going to be for the whole system. So M1 plus M2, that's the entire system, times the acceleration, has to equal M1G minus M2G, right? So M1 is going in the direction of the acceleration. We're going to consider it to be a positive force acting on the system. M2 is going against the acceleration of the system, so we're considering it negative, right? So this is our expression. And I believe for that question, it just says, find the acceleration, right? So part A for that problem was find the acceleration of the system. All right, so what is the acceleration equal? So just plug in the numbers, right? So we got here 1.5 kilos for mass 1 plus 0.5 kilos for mass 2 times the acceleration is going to equal 1.5 kilograms times 9.8 minus 0.5 times 9.8. I think it's also good to see it via algebra, right? So let's say we didn't even have the values. It's good to see how to write it out and simplify using just algebra. So here I would just divide both sides by M1 plus M2, right? So A is equal to M1G minus M2G all over M1 plus M2, right? And you can even simplify this further by factoring out the G. So if you needed to write this as expression, not that you have to for the test, but I think it's good to know. You can just write m1 minus m2 times g, right? All right, so that'd be the simplified expression. But, you know, you can do this just fine. If we have numbers, I think it's best to just plug it in numbers. I've noticed that students are less likely to make a mistake if they are able to do that. So let's solve this out. So 1.5 plus 0.5, we got 2 kilograms, all right, times the acceleration has to equal the weight of object 1. So let's actually calculate that out. All right, let's see here. All right, so actually for this calculation, I'm just going to use 10. And I think that's what they were using in the Classkick as well. So we're just going to say g equals 10 to simplify the calculations. All right. So we're approximating g as 10. That makes it easier to calculate by hand. So 1.5 times 10, we get 15 newtons. That's the weight of mass 1 minus 5 newtons. All right, so that's the weight of mass 2, right? So then we end up with 10 newtons. Makes it very easy to calculate. That's the net force acting on the system. And we have 2 kilograms times the acceleration. So the acceleration is 5, right? 10 newtons divided by 2 kilograms. We get 5 meters per second squared. All right. And there's that. And I believe the second part was how to use kinematics with the problem. So it says, how high above the ground was it if it hits the ground at 4.5 meters per second? So part B there was that the final velocity is equal to 4.5 meters per second. And we need to figure out how high up above the ground was it if it landed at 4.5. So to solve for this one, you're actually going to have to use the fourth kinematic relation. You're going to have to use this one, vf squared equals v naught squared plus 2ax. On the test, all you're going to really need to do when solving for acceleration is to use this equation, right? The definition of acceleration, delta v over t. So I'll give an example using that, but we might as well do the one from the Classkick because that's what we're doing. So to solve for this, it says that it starts from rest. So this is 0, v naught is 0, and we just got to solve for x. So then you have x is equal to vs squared divided by 2a, and then you just plug in the values, right? So 4.5 meters per second squared divided by 2 times the acceleration. The acceleration is 5 meters per second squared. Yeah, well, I guess I got to bust out the calculator anyways. All right, so let me get the calculator. So 4.5 times 4.5, 20.25 divided by 2 times 5, that's the same thing as divided by 10. All right, and I get 2.025, right? So 2.025, okay, meters. And if we use 2 sig figs, I believe that's how the answer was reported. So 2.0 meters. That's how high up it was. Let me give an example of when you instead of using the time-independent relation, what's an example where you'd use just the definition of acceleration? So let's say instead of how high it was, how long did it take to hit the ground? So VF is 4.5. It hits the ground going 4.5 meters per second. And how long did it take? Right, so when it says that, right, it's pretty much just asking for the time, right? So what was the duration of time for which this, mass 1 was actually falling? So again, we have the acceleration from before. We know the acceleration is 5 meters per second squared. We have VF. We know that V naught is 0. We're going to call going down, right? So it's accelerating downward. We're going to call that positive. And in that case, our delta V, we're going to say VF is positive. So we have a delta V over T. V naught is 0. So we have a delta V of 4.5 meters per second over 5 meters per second squared. And again, I got to use the calculator here. So 4.5 divided by 5, we get 0.9. So 0.9 seconds. And that would be an example where you just have to use the acceleration equation, right? Delta V over T. All right. So yeah, I think it covers pretty much everything you need to know. So Atwood's machines using, looking at free body diagrams for more than one object, right? So actually being able to do the individual, not just looking at only the systems approach, but also being able to break it down as the individual free body diagrams, like here. So basically getting the individual free body diagrams and being able to figure out what the net force is for each individual body, right? So that you got to know Newton's third law. The vertical motion stuff, the air resistance and elevators, we should be good on that. And then friction, right? I just really wanted to make sure that we're clear on the concepts for friction because there wasn't very much of that in the review. So yeah, anyways, with these examples, if you're able to follow and you know how to do these problems, you should be in good shape. Just look at the Classkick, go through the Classkick problems one more time, and then review the Kahoot PDF that I posted of the one that we did in class, and that's really all you need. So best of luck with studying, and hopefully we do very well on the test.